This video is going to be a review of doing loci with complex numbers. So I'm going to start off with my Argan diagram, which is obviously gives your complex numbers in 2D. And normally these questions are going to be to do with the modulus and argument of a complex number. So let's quickly review that. So if I stick a complex number z in the plane, then it has a real part and imaginary part. I can write that as x plus iy. Then its modulus is given by the distance to the origin, if you like. And the argument, remember, is this angle here that is normally rotated anti-clockwise from the positive real direction. Okay, so let's make a note of the range of values that we can have for our argument for. So our argument of z is theta, but it has to be between these two values. Okay, that's minus pi to pi given in radians. Okay, I'll list out some properties of the modulus and argument first of all, and then we'll kind of go through the different types of loci that we can possibly have. So first of all, modulus is multiplicative. So the modulus of a product is the product of the moduli. However, it's not additive. If you've got a sum in your modulus, then it's not equal to the sum of these, except it is less than or equal to that sum. Okay, this is a very, very famous inequality in maths. It appears all the time, but it's not in the A-level specification. Okay, thirdly, the nice property of argument that comes up quite a lot is this one. So the argument of a product is the sum of the arguments. Okay, and you'll notice that this property shares quite a lot to do with the natural log property. Okay, it looks a bit like a log when you do that. Okay, so the different forms of a locus then. If I give you a locus using combinations of these, you should be able to tell me what the shape it's going to make. So it's first of all worth noting that this expression, okay, if I've got a fixed complex number, okay, some kind of constant there, then this should be interpreted as the distance from this complex number. Okay, that's what I kind of say in my head when I see an expression like this. It's the distance of from this complex number here. Okay, but bear in mind what happens with brackets here. So if I've got z minus 3 plus 6i, then in order to interpret this correctly, I've got a bracket around this complex number here and write it as z minus brackets 3 minus 6i to distribute that negative. So this is then the distance from 3 minus 6i. Okay, so make sure that things are written like that if you want to interpret in a kind of geometric way like that. Okay, right, let's move to a new page. We'll do a few examples and then I'll do some exam questions and give you some practice. Okay, so the first type of locus that we can possibly have in a question will be something like this. Okay, so some distance given over here, and that's equal to something fixed like that. So this is clearly going to give a circle because our distance from our complex number here is fixed, so that gives me a kind of fixed radius around my complex number. So circle of radius r, that's the kind of fixed distance here, and then the center is our complex number z0. Okay, so I'll draw a quick picture of that. So you've got z0 as your center, and then a circle surrounding it with radius r. Now, when you draw a sketch, it's up to you to figure out whether or not the circle is going to intercept the axes and however many times that's going to occur. So your sketch has got to be reasonably accurate in terms of what it's doing with the axes. Let's put the radius on like this. There you go. Okay, so that's your first type. If I have two of these and they're equal to each other, let's do z minus z1 equals absolute value z minus z2. Okay, so reading this as we have on the previous slide, this is saying the distance from Z1 is equal to the distance from Z2. Now, as a locus, if I were to plot 2 points, then this locus with equal distances from those points is going to look like this. It's going to be the perpendicular bisector. Okay, maybe I'll do this solid so it kind of distinguishes it from the line I've just drawn. There you go. So that's the locus of points there. Okay, so normally if you've got some line that passes through this center point, then you'll be able to get that into Cartesian form. Okay, so it'll be some kind of straight line, so it'll be y equals mx plus c. Okay, remember Cartesian form is the form that involves x and y. Now, we might as well do that the same thing here for the circle, now we've done it. So if the circle has radius r, center z0, let's define z0. Let's say that that equals a plus bi. Then we can also get the Cartesian form as well, can't we? Because we know how to do the equation of a circle. So the Cartesian form for this first form is going to be x minus a squared plus y minus b squared equals r squared. There you go. Okay, right, let's look at another form then. So the third one I can think of is one that contains the argument. So in fact, I can probably combine this into a single one. Here you go. So the argument of z minus z0 equals, let's pick an actual value for this. Let's do pi over 4. Okay, so something of this type with a nice angle here for your argument. So this type is going to have a fixed complex number z0. And then the argument normally is centered at the origin, but this translation here is going to move our center across the z0. And then if the argument of z minus z0 is pi over 4, which is 45 degrees, then we're going to get a half line. So there's your locus. And the argument goes there. Okay, so let's describe this properly. So this is half line with half line from z0. If that makes sense. And then I'll put argument, bearing in mind that that's the argument given from that complex number and not the origin. Okay, there you go. Hopefully that makes sense. Okay, those are the three main types that you're typically going to get, and it tends to ask other things like maximum arguments in that locus and other things like that, but maybe we'll see that when we do some practice examples. Okay, if you want to take a screenshot of that, you can use that as a bit of a revision notes. Otherwise, let's move on to some proper examples here. Okay, where's my first one? Okay, great. All right, so finding a suitable Cartesian locus for the complex z-plane, shade the region that satisfies this inequality here. Okay, so z minus 3 absolute value less than or equal to the absolute value of z plus 3i. Okay, let's annotate this then. So the answer is already given, but I'm going to do my own annotation and show you what the steps are. Okay, so we know that this is going to give some kind of perpendicular bisector, at least when the two expressions are equal, and then the less than or equal to will give me some kind of region either side of that perpendicular bisector. You can probably see from the picture what's going to happen. Okay, so let's figure out what line we get when these two things are equal. So I'm going to, firstly, to get a Cartesian locus, I'm going to replace my z's with x plus iy, because that gets everything in terms of x and y. So if the absolute value of z minus 3 equals mod z plus 3i, then that tells me that x plus iy minus 3 equals mod x plus I y plus 3i. Okay. Right, now I can, if you like, group these terms together according to real and imaginary parts, and then I can get rid of the modulus by expanding out according to using Pythagoras. So bear in mind that the absolute value of x plus I y is the square root of x squared plus y squared. I'm looking to group things in terms of real part here and imaginary part here. So my next step is to do x minus 3 as real parts plus iy equals mod, and then the i's will go together, so it's x plus I lots of y plus 3. Okay, good. Right, now I can expand this out, and you've got to be careful here as to what's going to happen. So I'm going to get the square root of x minus 3 squared plus y squared equals the square root of x squared plus y plus 3 all squared. Okay, now if you like, you can take the square roots off straight away. However, if there's anything around these absolute values, you're going to maybe want to put the square roots in first of all. But if it's an easy question like this, you can just go straight to taking the square roots off. So I'm going to take off square roots. And then expand out, and hopefully it's going to give me something simple that tells me what this locus will look like when they're equal. So x squared minus 6x plus 9 plus y squared equals x squared plus y squared plus 6y plus 9. And then lots of cancelling. X squareds go, and then the y squareds go as well. And then also the 9s. Okay, so what have we got now? We've now got 6y equals minus 6x, which is the same as y equals minus x. Okay, or as it's given over there, x plus y equals 0. Okay, so now I know what my boundary line is for my locus. I can then draw it and then figure out what's going on with the less than or equal to. So I'll maybe cover over this answer box. Okay, so we'll draw on our locus. Okay, y equals minus x, I can easily draw that. That goes like this. Okay, drawing it solid as well because our inequality is inclusive. Okay, what you might want to do as well is looking at the original form, we can plot the points that we've bisected as well. So this is distance from 3, and 3 is a real number, so it goes here, is the same, or I should say less than or equal to the distance from minus 3i. Remember that this is the same as z minus 3i. So putting that double minus in gives us the other centre there. So our other complex number is here, minus 3i. So now I can decide which side I want to be on because my distance to 3 has got to be less. So if I'm closer to this side, that means that I must be on this side of the line. So I'm shading in the correct side here. Okay. Again, that's because the distance to 3 given over there is less than the distance to minus 3i, which is given down there. Okay, perfect. That's the first one done. And oh, I should say, I should probably finish off properly by shading it in with R. There you go. There you go. Okay, great. Now, I'm going to skip over some solving of polynomials questions here because I'm going to leave that to a separate lesson. So we'll skip over that one. I'm also going to skip this one. If you want to look at this one, it's slightly different. You can look at the answer box to see what's going on with that one. There was one I had that was a circle. Here we go. This circle one's got quite a good one to do. Okay, so we want to sketch the locus of points that satisfy mod of z minus 1 minus I equals 4. And then we want the minimum and maximum value of mod z for points on that locus. Okay, let's cover over. I don't want to cheat quite that much. Right, let's see what we've got here. So I'm going to rewrite this in a way that I can kind of interpret it geometrically. So if I bracket around this complex number, I'm going to get 1 plus I which tells me that the distance from 1 plus I equals 4. That's the circle. Centered at 1 plus I, and the radius is 4. Okay, don't be swayed by the fact that this is a square number. That is the radius, not the radius squared. Okay, right, so I can plot that now, and I'm going to do it reasonably accurately and think about what's going to happen with the intersection with the axes. Okay, 1 plus I is about here. Now, because it's only 1 by 1, if I've got radius 4, that's going to intersect the axes quite a lot. So I'm going to draw it quite big, round like this. I should probably do. There you go. All right, not particularly great, but there you go. There's a circle or close enough to 1. Right, 1 plus I is the center. The radius is 4. Okay. Okay, that's all sketched. The minimum and maximum value of mod z then. So mod z is going to be the maximum and minimum point on here that gives those maximums and minimums. And what's going to happen is, seeing as it's going from the center, the minimum is going to be the one that gives us closest in. So going through the center, the origin will give us the minimum down here. We'll call that z minimum. And then coming out this way is going to give us z maximum. Okay, so you want to be using the center point there and the origin in order to work out those minimums and maximums. Okay, right, with a bit of thinking about geometry here, I can work out these distances quite nicely. So I can firstly think about this distance using a better brace than that, I should say. So that distance there is 1. And then this distance here is also 1. So that means that the hypotenuse length here will be root 2. That's from very quick Pythagoras. Then the radius here is going to be 4. And that gives me pretty much all that I need to work out these absolute values. So the absolute value of z minimum will be the distance here to the origin, but that's going to be the radius minus this root 2. And the maximum will be root 2 plus 4, because I've done this length here to get to the center point and then another radius. Okay, great. That's number 1. That's the first one done. Okay. Right, I'm gonna be finding one more to do, and then I'll leave you to do some yourself. I'll find one. This one here is quite a good one because it's quite uncommon to see numbers outside these absolute values here. So we're going to show that this locus here gives rise to this Cartesian form for its equation there. Okay, again, cover up the proof. All right, so these are equal. I'm going to replace z with x plus iy. And then proceed as before, but you've got to be careful about what happens with this 2 when you get to it. So now x plus iy minus 1 equals 2 times, and then absolute value x plus iy plus 2. Okay, now let's let's group terms together, shall we? So that's x minus 1 plus iy equals 2. And then it's x plus 2 plus iy. Right, now I'm going to expand out, but I'm going to stick to using the square roots this time. So the square root of x minus 1 squared plus y squared equals, and then the 2 will still be there, and then this square root here, x plus 2 squared plus y squared. Okay, now I've done that in a way that stops me from not squaring this 2 here. If I want to get rid of these square roots, I have to square everything, so the 2 will square as well. So now we've got this, x minus 1 squared plus y squared equals 4 lots of x plus 2 squared plus y squared. Okay, it's quite important that you do that step properly in order to avoid that mistake. Okay, now I'm going to distribute and expand. So the left-hand side will look like this. It will be x squared minus 2x plus 1 plus y squared. And then sorting this stuff out will give me, right, 4x squared. And then 4 times 4 is 16. And then 4 times 4 is again 16. And then 4y squared. Okay, right, let's do some simplification here. So I can get everything over to the right-hand side. Looks best to do. So 0 equals 3x squared. And then that gets rid of the x squareds. I'm going to have 18x if I combine x's. And then I'll have 15 for my number part. And then I'm going to have 3y squared. So let's get rid of those, and then 3y squared. And then we're done. Okay, right, that's quite nice because that means we can divide it all by 3. So dividing by 3 gives us x squared plus 6x plus 5 plus 1y squared. And now I'm looking ahead to where I'm trying to get to. I'm trying to get to this circle form, and I think best thing to do is complete the square so I can then get it into that shape. So I'm going to now do x plus 3 squared. That will give me plus 9, and I want to do minus 4. And then there's my y squared, and then we're done. Okay, so loci like this typically will give you a circle because it involves the same steps that lead to this kind of expression down here. All right, perfect. If you need any more help, I think the ones that you might need any more help for are the maximum, minimum, argument and absolute value questions. I might make a separate video doing a couple more examples there, but I'll leave it there for now for this video. All right, thanks. Enjoy your lesson. See you soon.